everyone, this is Rashmi here. I hope you guys are doing safe. Stay safe, wash your hands, follow the protocols, be wary of yourself and others. So today what we're going to do is synthesize methyl diantilis. It's a 2-week experiment which we were supposed to do if you guys were here. So we are going to today show you how it's done. So methyl diantilis is a compound that is used as a flavoring agent, especially since it has the spicy vanilla smell. We all know that vanilla flavor is one of the most common flavor out there, and vanillin is the compound that provides that flavor to it. So one of the derivatives of vanillin is ethyl vanillin, right here. So what we are going to do, we are going to use this ethyl vanillin to synthesize methyl diantilis. So it's a 2-step process. This process is currently used by Givaudan to synthesize the compound. The first step is converting this aldehyde into its corresponding alcohol by using sodium borohydride reduction. It's a very common reduction technique for reducing aldehydes, any carbonyls, even acids. The whole reduction is done under alkaline condition. So what happens after we get this alcohol, after reduction, we are going to isolate it. We are going to figure out its melting point and things like that, and then we are going to convert this alcohol to its corresponding methoxy group in the next step by using methanol and amber list 15 as a catalyst. So this is part of week 2, and this is week 1. So in the week 1, as I mentioned earlier, we are going to do the whole reaction in alkaline conditions. So of course we need to neutralize it, and for that we are going to use 2.5 molar HCl. And the moment you're going to neutralize your reaction mixture, there'll be a lot of white foams and froth going on. So you have to be careful about that. And of course, you have to make sure your pH is slightly acidic. It's not about how much volume you add, it's all about the pH maintenance. So after you're done with the reaction, make sure your pH is acidic a little bit. You have to test it with your pH paper. If not, you're going to lose a bunch of your compound. So after you get this, how do you know that your reaction is complete? To do that, we're going to monitor the reaction using thin layer chromatography, which is TLC. You guys have done it before, I'm pretty sure. So let's say A is our starting compound, ethyl vanillin, and B is our ethyl vanillin alcohol. So we are going to take tiny bit of solids that we'll get before and after the reaction and dissolve it in acetone and spot it on the TLC, elute it, and see how far the reaction has reached completion. Ideally, if the reaction is 100% complete, we should not see any of our A or the starting compound in our second spot. That's our ideal scenario. If it does, you can always write it in the manual or in your lab report that it's not complete. The second step is also, we're going to similarly monitor using TLC. Of course, what we're going to do, we're going to pull out aliquots every now and then and test whether the reaction is complete or not. If it's not, we're going to continue the reaction. If it's done, that's great. Then we're going to go for our next step. Yes, so we have to be careful about certain things. This catalyst can become very dry very quickly. So while weighing out, we have to weigh out very fast. And this neutralization step is crucial. Be careful with the HCl and with the white froth. You don't want it anywhere on your clothes or on your hands. And that's about it.
Yeah, hey everyone. So hopefully you're all staying safe. So just a few things for the experiment also. We'll be showing you small clips as we go along so that you can take notes. Make sure you take very good notes of the things that are happening. We'll probably, if we weigh something out, we'll probably tell you how much it is before we add it. So you just write down your observations, what you see, and things like that. Hopefully we don't make this into a very long video. Like I said, we'll try to show you small clips that we'll label so that you know how to follow this video basically. All right, so that's about it. So let's get started.
So we added ethyl vanillin and with sodium hydroxide. We are supposed to stir it for 5 minutes with the stopper on and dipped in an ice bath. So after this stirring for 5 minutes, we are going to add our sodium borohydride, and also just for the record, I took about 1.640 gram of ethyl vanillin as my starting material. So please record it down. You'll need it for your final yield. So we have stirred our ethyl vanillin with sodium hydroxide for about 5 minutes now in an ice cold condition. So now we're going to add our sodium borohydride in portion wise and stir it. So you need to add it slowly.
For this portion, we weighed about 0.306 grams of the sodium borohydride that we're currently adding. Just make sure make note of the color as well, if we didn't mention that before.
Yeah, the color definitely turned a little bit more yellowish, a darker color after addition of borohydride and after stirring it for 5 minutes.
Was there solid on the?
So no, it's clear actually.
Yeah. So your manual says that maybe not all of the starting material will dissolve, but here we are seeing that it's basically everything dissolved. So there might be a few bubbles in there that might throw you off.
You can show it here.
If you can see there, some of that is ice and some of that is just little air bubbles.
Yeah, it's mostly clear, so.
Yeah, mostly clear. Okay, so right now we're just going to add the reflex condenser and basically going to keep stirring that for another 30 minutes. So once the 30 minutes are done, we'll be back.
So we have added sodium borohydride and our ethyl vanillin and kind of stirred it for 30 minutes. As you can see here, the reaction mixture is yellowish and it's kind of clear. There is no solids that I can see here. And so after putting the condenser on and keeping it stirring for 30 minutes at room temp, we have put the ice bath in here. And then now we're going to add our 2.5 molar HCl. So here I have 10 mils of 2.5 molar HCl, and I'm going to add 1 mil at a time from the top of the condenser. So it's supposed to generate a lot of foam and froth. I can see it's generating the foam where the acid is hitting the solution. I hope you guys can see it too. You have to be careful with this. You don't want the froth to be so high that it should not be reaching the condenser. So you need to stop adding once you see it vigorous. So now what I'm going to do is check the pH of the solution. The easiest way to do it is to lift the condenser, kind of stir our solution in here. You don't want to check the pH of the foam because that will give you errors. Then put it back in. And here I have our pH stripped. If it turns red, that means it's an acidic, but here it's green, which means that it's still alkaline and we need to still add more acid to our solution. So we'll get back after adding more and more acid, and we'll keep on continuing doing this. Hi everyone, we are back again. So our solution I added about 9.5 mils of our 2.5 molar HCl. So we are going to check the pH now, whether it has turned completely acidic or not. The best way to test it is to take a glass rod, as mentioned earlier, just stir it a little bit and kind of take it out and put it on the pH paper. As you can see, the pH paper turned red. So it's not the foam. If you're unsure whether it's a foam, maybe stir it again, add a couple of drops of water into your mixture and test it again. As you can see, this is red, so now that means our mixture is now ready for our workup, and it's completely acidic. And we'll get back to you soon. So we are back with our reaction product right here. As you can see, the white foamy stuff, which is under acidified condition right now, we need to isolate our product using vacuum filtration. So this is the vacuum filtration setups. We have two filter flasks on the both sides. You guys have used it before in this semester. So what we're going to do, we're going to rinse our filter paper with cold water and pour our solid reaction. Now we are going to pour our reaction mixture through. We're going to rinse it with some little water. Try to transfer as much as possible. This one does not dissolve in water, so there is no chance of going inside. Maybe scrape the sides a little bit if you want to transfer all of it. And press it gently down to ensure maximum vacuum. And we're just gonna wait till it gets dried, and we'll be back soon.
So hey everyone, so we're gonna do the TLC for part 1, which is the reduction of our aldehyde. So here in our TLC plate, like Rashmi showed you, we have 8 and B. So 8 is actually our benzaldehyde, our starting material. So we're going to take that and we're going to spot here. That should be good enough. And next we're going to spot our product, our reduction or our alcohol. That should be enough. And then again, just like last time, we're going to develop it and we'll show you the outcome in the UV, and we'll show you the distances so that you could calculate the RF values. That's it. So hey everyone, so we're back with part 1 for our TLC. So this is the conversion of our aldehyde into an alcohol. So two things, when we take the TLC, we know that we have two very different functional groups, so we can also deduce what the outcome should be, right? So we know that an alcohol group is more polar than an aldehyde, so we should expect the alcohol group to remain at the bottom and the aldehyde group should move further up the column. So let's see if that's what we have. So now I'm going to circle the spots, and then I'm going to take the distances so that you can calculate the RF values. Okay, just as we predicted for spot A, which is our benzaldehyde, the spot moved up further in the column or in the TLC plate, whereas the alcohol group actually is a little bit more polar, so it hangs onto the silica more, and so it's down here. So we know that we have no other starting material because there's none on top. So we know that the conversion, or we had a 100% conversion.
Hi everyone. This is the last part for our week 1 experiment of methyl diantilis. So we are wrapping up the experiment, and I'm going to talk a bit briefly about the conclusions from today's experiment. So as I had shown previously from the vacuum filtration setup, while we were going through all this filtration, we obtained white solids, which is very powdery for our as our ethyl vanillin alcohol, and it's kind of wet, and we took the melting point, and the melting point is about like 55 to 59 degrees C, which might be because like it's still wet, and it still has moisture in it and things like that. So this is the amount of ethyl vanillin alcohol that we got, about 1.12 grams, which will be used for our next part of the methyl diantilis experiment. And this is the TLC that has the initial product, ethyl vanillin, and the final product, ethyl vanillin alcohol. Make sure you note down the numbers. This is the measure of the distance from this spot till this line over here. So you know how to calculate the RF values, where you divide the distance of the solvent front comes in the bottom, and the distance, and this distance comes in the top. So this distance divided by this distance give you the RF value. Make sure the RF value should be less than 1. If you're doing it the wrong way, it can be greater than 1. So just to make sure you take care of that. So these are the different amounts of sodium borohydride, the starting material that we took. So from there, you can calculate your percentage yield. Just write down whatever we mentioned during our short videos and the clips, and we'll see you in part 2.